So today we can go to lesson 7, the last lesson of this semester, Dispersion Management. Okay. There are 4 sections in this lesson, starting with material dispersion. Okay. You have studied some of the materials in lesson 3. When we talk about light-matter interaction, we treated material dispersion there. Okay. Then it's something new, temporal dispersion based on angular dispersion. This is something new, angular dispersion. We will define what is angular dispersion and why is it related to the temporal chirp that we have been familiar with. Then in section 7-3, we will talk about grating pairs. This is a traditional post-compressor used in dispersion compensation. Okay, it's still used today. Okay, and usually you can create a very large compression ratio or stretching ratio by using grating pairs. Previously, we spent the last section about prism pairs, but in view of the tendency that chirp mirrors become more and more popular instead of prism pairs, so I replaced the last section by chirp mirrors, which is a very different geometry. Okay, it can provide dispersion compensation, but with very different geometry. Okay. So let's start with material dispersion, including material dispersion formalism and properties. Okay, I believe you must have been familiar with this picture. GDD-induced spectral phase modulation. Assume we have a transform-limited input pulse. So in the time domain, you have an electric field like this. Fringe density is nearly constant. And this is frequency domain picture. The blue curve is the power spectrum. The red dashed line means the spectral phase. Since this is a transform-limited pulse, so your spectral phase is a constant function. Okay. After the pulse passes through a dispersive medium, this is the output pulse. We know in the time domain, the pulse will be stretched and becomes chirped. So the fringe density varies with time. In this example, fringe density increases with time. So this is an up-chirped pulse, assuming the medium is normally dispersive. How about the frequency domain? The blue curve does not change. The power spectrum is the same. But you will have maybe parabolic function for your spectral phase because different colors propagate at different speeds. So accumulated phase will be different, frequency dependent. Okay, so that's why you have a stretched and a chirped pulse in the time domain. Okay. So the picture is about qualitative description. How about quantitative analysis? This is the only formula we need. The corresponding spectral phase modulation, say it's designated by psi of omega, equals minus beta of omega times L. L is the thickness of the medium. Okay, it is a constant. How about beta of omega? We know it means propagation constant of the medium, which is usually formulated in this way. Okay, omega times index of refraction over light speed in vacuum, c. Okay, basically it's index times wave number in vacuum, omega over c. Okay. And then you can identify beta of omega is actually a nonlinear function of omega as long as your medium is dispersive. What is the meaning? The medium is dispersive. It means n of omega is a function of frequency. And then you have omega already there, so the product must be nonlinear as long as n is not a constant. It's a dispersive medium, you got a nonlinear function of beta. And this formula tells us if you have nonlinear function of beta, you have nonlinear spectral phase modulation, starting with second order function, parabolic function. You can have higher order terms, of course. If we restrict ourselves to third order approximation, the spectral phase modulation function can be represented by second order contribution proportional to omega squared, and the third order contribution proportional to omega cubic, where these two coefficients, psi 2 and the psi 3, are related to beta 2, beta 3 in these two ways. Okay, so basically proportional to thickness. Okay. And in this slide, I try to demonstrate the dispersion formulas both in variables omega and the variable lambda. Okay? The relation between omega and the lambda is shown here. Okay? Omega is angular frequency, which is 2 pi times non-angular frequency f, or nu, right? And we also know the formula. Frequency f equals light speed c over wavelength lambda. So omega and the lambda actually are related in this nonlinear relation. Okay. So if you take first order derivative, what can you have? If you check this formula and performing first order derivative with respect to lambda, okay, so you have d omega over d lambda to the left-hand side. How about the right-hand side? Derivative with respect to lambda. 2 pi c is just the constant, so you are actually calculating 1 over lambda derivative, which is minus lambda squared, something like that. But by taking inverse, you got d lambda over d omega equals this one, minus lambda squared over 2 pi c constant. We will use this relation later. Okay? Then let's see what is the relation of between n prime of omega and n prime lambda. The definitions are, this is first order derivative of index of refraction with respect to variable omega. And this is derivative with respect to variable lambda. They are different, right? So you can use chain rule, okay? n prime omega equals dn over d lambda times d lambda over d omega. This is chain rule, okay? And n lambda, you got n prime lambda. And d lambda over d omega, you can borrow this formula we just derived. So together, you got this relation. Okay. Any question? It's just chain rule application. Then we can further the derivation to second order derivative, n double prime of omega. By definition, this is another derivative with respect to omega of n prime, right? But n prime is already here. So you can apply chain rule for this relation again, okay? And I skip the intermediate steps. This is the result. In the end, you got something like this, lambda cubic over 2 pi squared c squared constant times the summation of two terms. The first one evolves with n prime lambda, first order derivative. The second term involves with variable lambda times n double prime lambda, second order derivative. Okay. And the last one should be the same, the third order derivative. You got an even longer equation. Okay. So any question about the derivation processes? Okay. I think it's trivial. Then, how can we know these formulas are useful? Okay, say let's take a look at two examples. The formulas about group velocity Vg and the formula about GVD parameter beta 2. Okay. By definition, what is group velocity Vg? You have known this. It's 1 over beta prime, right? Do you still remember how to derive this formula? There are different ways you can arrive at this. So let's just assume you know that. And the beta prime of omega, you can borrow the relation between beta and the index, which is here. Okay, so you have to calculate first order derivative for this relation. And there are two functions of omega. One is linear function omega, the other is index of refraction, n of omega. So the derivative is omega prime equals 1 times n plus omega preserves times n prime omega, right? And you need to access this formula, n prime of omega. Okay, and if you do that, you got this. Okay, c light speed in vacuum over n of omega 0 plus omega 0 times n prime omega 0. This is the formula of group velocity in terms of angular frequency. But you can also use this relation such that you got this one. Okay, this is the group velocity formula in terms of variable wavelengths lambda. Okay. Let me ask you, what is this? Forget about mathematical derivation. Say this is true. Then what is the meaning of the denominator? Group velocity Vg equals light speed in vacuum c over something. What is the meaning of that something? Pass? Truly? Okay, let's check the physical units. Okay, this is speed. So SI units should be meter over second, right? If it is pass, the physical units is meter. So after the division, what do you have? 1 over second, which should be hertz. But this is Vg, the physical units should not be hertz, right? So the denominator cannot be pass or anything regarding length, right? What is the physical units of denominator? No unit, right? Because Vg and c are both velocities. Okay, so this is a quantity without any physical units. So what is that? Yes, equivalent index or usually group index n sub g, right? And you can see group index is different from the index here. N of omega 0. This is index. And the group index is different from index because of the modification term, right? You have a modification term here. It can be a positive or a negative number, depending on what? Depending on this one, right? N prime. Derivative, if it is a positive slope, you got a positive modification. So your group index is bigger than index. So your group velocity is faster or slower than phase velocity? Slower, right? Larger index, slower velocity. So if m prime is positive, you have a group velocity slower than phase velocity. In other words, your envelope propagates slower than your carrier. Okay, and if you have a negative derivative, negative slope, you got the reverse. Okay, and this is also the group index. Okay, and the sign of modification term depends on m prime lambda. Okay, and you got a similar story. Second formula, GVD parameter, okay, beta 2. Beta 2 is just second order derivative with respect to second order derivative of beta of omega with respect to frequency omega, right? And you can repeat the process in the end. If you write it down in terms of variable omega, you got this. And if you apply m prime substituted by this one, n double prime substituted by this one, you got a simpler formula, which is just a constant times n double prime lambda 0. Okay, and then this is equation 1. We might need to access this formula in the future. So what can we know from these derivations? GVD parameter, beta 2, can be evaluated either in this formula or in this formula. And usually the later one is more popular because it evolves with a single second order derivative only. If you want to use the first formula, in addition to second order derivative, you need to know first order derivative as well. So this is a coincidence. When you try to calculate beta 2 GVD parameter, this is more usually used. Okay, any question? Next, first order dispersion or second order spectral phase. You have seen the same picture before, okay? Say you have input pulse, the green one, transform limited pulse. In the frequency domain, you have a broad spectrum from red color to blue color. And if we define omega 1 means some lower bound of your frequency components, omega 2 is some upper bound of your frequency components. Then the difference between omega 2 and omega 1 should be delta big omega, the bandwidth, which is inversely proportional to the input pulse duration. Okay. If this pulse passes through a dispersive medium, at the output, you got a stretched, chirped pulse. And how to quickly estimate the output pulse duration? You have the experience already. Just evaluate how long does the high frequency components take to travel through this medium. This is tau g of omega 2, the group delay at frequency omega 2. Then minus the group delay of frequency omega 1, the time required by the lower frequency component to pass through the same medium. And the temporal difference should be about the output pulse duration, right? This is the underlying idea. So output pulse width formula is approximated by tau g of omega 2 minus tau g of omega 1. And the tau g formula is here, beta 1 times L, but this is a constant independent of frequency. And you have another term, beta 2 times L times frequency, omega. So if you substitute omega 2 and omega 1 into this formula and subtract them with each other, you can see the contribution from the first term will cancel with each other. Only the second term remains. And you got beta 2 times L, the slope, times frequency difference, which is the bandwidth as we just defined, delta big omega. So this is the formula. Beta 2, the GVD parameter, times medium thickness L, times the bandwidth of your signal. Then you can estimate the output pulse width. And we also know the same idea can be applied to this case. Still, output pulse width equals another newly defined GVD parameter, big D, times the same thickness L, and times the bandwidth. But here, the bandwidth is replaced from delta big omega to delta lambda. Because if you use a spectrometer, the bandwidth you can have from your apparatus could be like this. The bandwidth in terms of wavelengths. So if you change this one, okay, the corresponding GVD parameter will be different from beta 2 to big D. Okay? And then you can equalize these two formulas. You can find the relation between big D and the beta 2, which is differed by a ratio, delta big omega over delta lambda. But the relation is fixed, so you can derive this formula or this one if you substitute the formula of beta 2 in the previous slide. You've got equation 2. Okay. We will use equation 2 in the future. Okay. So, any question? 所以这边讲的只是利用这个 picture， 也就是highly chirp pulse 它的宽度的公式，你可以推导出另外一个 GVD 参数 big D， 它跟 beta 2之间的关系。那 beta 2的 formula 有 ，big D 的 formula 就跟着有。反正它们都是跟折射率的二次微分有关。